Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay, the 1983 work by Edward Witten, entitled Supersymmetry and Morse Theory, stands as a landmark contribution, weaving together theoretical physics and mathematical topology in a manner previously unseen. This exploration, penned at a juncture where both supersymmetry and Morse theory were fields in dynamic development, proposed a surprising connection, generating significant interest and providing new perspectives on existing problems. This essay aims for a thorough evaluation of Witten's claims, the arguments presented, and the methodology, dissecting the paper section by individual section to render a full assessment of its significance. It's an analysis designed for those deeply familiar with the mechanics of theoretical physics and mathematical reasoning. Our focus rests firmly on the internal logic, evidence, and implications within the work itself, acknowledging external elements solely as they illuminate the integrity of his core arguments. Section 1: Introduction and Overview. The introduction provides an important groundwork for the subsequent arguments. Witten establishes the central premise: a supersymmetric quantum mechanical system can be constructed whose ground states are in correspondence with the critical points of a Morse function defined on a manifold. He initiates this by linking the index of a Dirac operator, calculated using supersymmetry, to a topological invariant. The choice of a Dirac operator is essential. The concept of supersymmetry is used to formulate a quantum mechanical system. The paper provides the essential elements demonstrating the utility of supersymmetry as a computational tool in understanding topological features. The introduction deftly sets up the relationship between a supersymmetric quantum mechanical system and Morse theory, presenting the fundamental idea that the ground states of this system correspond to the critical points of a Morse function on a manifold. The index of an operator becomes a unifying element, providing a bridge linking the analytical aspects derived from supersymmetric quantum mechanics with a topological invariant. The claims begin here: the suggestion that supersymmetry can provide a fresh approach to calculating topological quantities. The approach is framed so that Witten is not aiming to construct a comprehensive theory of everything, rather, a means for solving existing problems by exploiting a known symmetry. This establishes the focus on a specific target, giving the paper its shape and its function. The introduction foreshadows the core move: the use of supersymmetry to streamline calculations in the realm of topology. Section 2: The supersymmetric quantum mechanical system. In this section, Witten constructs the supersymmetric quantum mechanical system. The Lagrangian is explicitly detailed, incorporating the fundamental operators necessary for formulating the supersymmetric model. The Hamiltonian emerges as a critical construct, its form directly related to the existence of supersymmetry. The properties of this Hamiltonian, notably its non-negativity, become paramount. The key claim here involves the definition of the supercharge operators, generators of supersymmetry. These operators, denoted conventionally as Q and Q dagger, have a particular algebraic structure reflecting their role in the symmetry. The construction of the Hamiltonian, proportional to the square of the supercharge operators Q dagger Q plus Q Q dagger, is fundamental. This construction guarantees its semi-positive character. Consequently, the ground states of this system are those states annihilated by both Q and Q dagger. The analysis rests on the observation that these ground states encode topological information, which is the core of the relationship to Morse theory. The system becomes a probe. The existence and characteristics of the ground states will indicate topological invariance. The argument relies on the directness of the relationship between the Hamiltonian and supercharges. The energy of any state is, by construction, assured to be a non-negative quantity. The paper makes the case for how the physical principles of quantum mechanics and the specific requirements of supersymmetry intertwine. The argument is founded on the formal mathematical structures, which are then carefully applied to the quantum mechanical system, Section 3 Morse theory, and the Witten complex. This section establishes the connection to Morse theory. Witten introduces the Morse function, h, on the manifold. The gradient of this function, defined to be minus grad h, is key. This sets up the mapping where critical points h are linked to a quantum mechanical system. The introduction of a parameter, t, which will be central to the connection between the quantum mechanical system and Morse. The central assertion in this section is the definition of the Witten complex and its connection to the de Rham complex. The Witten complex is the mathematical structure where the differential is modified by the Morse function and the parameter t. The differential is given as an operator that maps differential forms of certain degrees to other forms of a different degree. The key here is that, at large T, the Witten complex is approximated by the Morse complex. The argument builds the bridge between the supersymmetric quantum mechanical system and topological properties of the manifold. The argument depends on taking the large T limit of the quantum mechanical system. The result will be, in the limit, a set of states. The claim is that the ground states of the supersymmetric quantum mechanical system, in the limit T moves towards infinity, are in direct agreement with the critical points of the Morse function. In the approach, the authors make the case that the supersymmetric quantum mechanical system is equivalent to the Morse theory, particularly at large. Section 4. The index theorem and its interpretation. This section focuses on theorems related to the index of the Dirac operator. The index is central to associating the quantum mechanical model to topology. The index of an operator is a measure of the difference between the number of its zero modes. Its value is, generally speaking, a robust topological invariant. In an algebraic sense, it provides a link to the Betti numbers of the manifold. The Witten paper explores the index theorem. The theorem describes an operator, Dirac, such that the index of the Dirac operator is related to the geometry of the manifold. The index of the Dirac operator, calculated within the supersymmetric system, is identified with the Euler characteristic of the manifold. The Euler characteristic can be determined using the Betti numbers of the manifold. The core claims rely on linking the index, computed using the quantum mechanical approach, with the Euler characteristic. This involves relating the zero modes of the Dirac operator in the quantum mechanical system with the concepts of the Morse complex, critical points, and finally, the topological invariance. The argument demonstrates that the index theorem in this context, more than a mathematical curiosity, it is the essential idea here is the use of a symmetry to simplify a calculation. The introduction of supersymmetry allows Witten to relate the index of the Dirac operator. The argument demonstrates how supersymmetry acts as a shortcut, simplifying a computation that would be greatly complicated in the absence of symmetry. The key innovation is creating a physical model where calculations give results about topological invariance. It transforms a problem. Section 5 Examples and Applications. This section provides concrete examples to illustrate the concepts. Witten applies the established formalism. These examples offer a demonstration of his abstract ideas, meeting the utility of the framework TAND. The specific example focuses on the two-dimensional manifold, analyzing the behavior of the system on the manifold. The core claim is that the analysis, as applied to these examples, consistently reflects the topological invariance of the manifold. The ground states of the supersymmetric system precisely match the critical points identified through the Morse function. The examples confirm the correspondence between the quantum mechanical analysis, the Morse function, and the topological invariance. The approach is not to solve pre-existing problems, but to show that an algebraic structure can inform calculations. The section serves to cement the priori claims by applying the theoretical arguments in an explicitly calculable context. These examples, instrumental in making his arguments more convincing and accessible. The worked-out examples are a crucial element in the success of the paper. Section 6 Extensions and Further Directions. Witten goes beyond the basics in this section, discussing possible extensions and further directions. The goal here are not to solve everything or to expand on the scope of the central The paper considers the implications of the framework as it can apply to a wider variety of manifolds. The approach explores an expansion of applications beyond the core examples, opening up new avenues of exploration. The key claim is not a single theorem, but a collection of avenues. It suggests that the framework is general and can apply to many different situations. The suggestion is that the system has the potential for new developments, and there is a potential to discover new topological invariants. The arguments are based on the general nature of the tools. The paper is built on Section 7 formal proofs. The final section contains rigorous mathematical proofs. These proofs confirm the validity of the main claims. These proofs are not just a formality, but the core of the argument, providing concrete arguments under a system. The authors present the core mathematical theorems that undergird the entire argument. The central argument is the proof of the relationship between the supersymmetric system, the Morse function, and the topological invariants. The proofs explicitly demonstrate the equivalence between them. Every step is logically and mathematically justified. The proofs are essential. The significance of the paper depends on the validity of these proofs. The paper demonstrates the internal consistency of the claims. The argument is that the mathematical relationships have been rigorously demonstrated. Conclusion. In summary, Witten's supersymmetry and Morse theory presented, without the constraints of negativity or comparison, a remarkable synthesis. It showed that supersymmetry, a concept previously investigated within the realm of theoretical physics, could supply a valuable tool for the study of topological invariants. The paper's main thrust centers on establishing a precise mathematical correspondence. The central assertion that is shown is the index of a Dirac operator, computed within a supersymmetric quantum mechanical system, precisely mirrors topological invariants of a given manifold, specifically the Euler characteristic. The power of the argument presented is the way the physics is used to find a new means of analysis. The introduction of a parameter, t, provided a conceptual bridge, connecting the quantum mechanical system with Morse theory. The paper's elegance comes from providing a fresh perspective, enabling novel approaches to problems previously addressed. While the mathematical machinery of supersymmetry and Morse theory were well established, Witten's success lay in showcasing an unexplored link. His approach to the subject provided a new way to look at the relationship between topology and physics. The work's enduring significance is multifaceted. It provided a conceptual blueprint, a pathway that has since inspired a wide array of research. The paper is a profound demonstration of the power of interdisciplinary thinking, illuminating the depths of both theoretical physics and mathematics. This work stimulated further studies as researchers tested and expanded the framework in various contexts, including condensed matter physics, string theory, quantum field. The internal claims from the construction of the supersymmetric quantum mechanical system through to its connection with the Witten complex and the rigorous mathematical proofs are presented cogently. The methodology, predicated on the employment of supersymmetry as a computational shortcut for the calculation of topological invariants, is both innovative and compelling. The paper not only presents a clear argument but also provides a collection of examples. The paper's contribution is not merely in the technical details, but also in the paradigm shift it introduced. The paper's lasting impact bears testimony to Witten's insightful approach, which has provided insights and inspired work in both mathematics and physics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.